So yes, I'd like to introduce Berardi Sensale-Rodriguez from the University of Notre Dame. He's a PhD student there, expecting his degree in May 2013 coming up. Before joining Notre Dame, he was a student at the University de la República in Uruguay. He has 13 journal publications, including one in the prestigious Nature Communications, and his research area is terahertz high-frequency electronics, development of new terahertz high-frequency electronics applied to biomedicine, security, and communications. So with that, I will hand it over.
Okay. Thanks a lot, Shamesina, for the introduction. Okay, so let's get started. Okay. Good afternoon, everybody. It is actually great to be here in Salt Lake City. Okay. Thank you for giving me the opportunity to share with you some of the research we're making in Notre Dame in terms of terahertz and high-frequency electronics. For those of you who are not familiar with this field, this is an area with an amazing set of challenges, which also means an amazing set of opportunities. Here there is an outline of my talk. I'm going to start with an introduction to terahertz technology, go through its history, applications, and challenges. Then I'm going to introduce two families of devices we have been proposing and demonstrating in Notre Dame. First, reconfigurable terahertz components based on atom-thick graphene. And second, high-frequency electronics based on a non-traditional transport mechanism, basically waves of electron density which can travel faster than the electron drift velocity. Finally, I'm going to share the research directions I am envisioning for my future. So, the terahertz range is basically the region of the electromagnetic spectrum between the microwaves and the infrared. At these frequencies, both electronic and optical phenomena are significant. This is the reason why terahertz is often considered the melting pot between electronics and photonics. The wavelength of terahertz radiation is in the order of hundreds of microns, and their energy is only a few milli-electron volts. What happens in this region of the spectrum has been historically very fascinating and intriguing, as we can see from this physical review paper from 1897. Since then, people have been wondering about what happens in the region separating optical and electrical phenomena. Today, terahertz is a growing market, which is expected to reach $500 million in 2020. We see that it's currently undergoing a transition from being mainly research applied, in particular in astronomy, to be a very diversified market with a lot of applications. So let's look at some of its applications. And for this, we are going to go back in time to the time of the Big Bang, the origin of the universe. And we are going to look at all the photons which have been emitted since that moment. If we count them and we sort them per region of the electromagnetic spectrum where they belong, we can see that 98% of these photons lie at terahertz or far infrared frequencies. So no wonder that from this point of view, astronomy has been historically the most traditional field of application of terahertz technology. Here we can see the typical radiated power versus wavelength for an interstellar dust cloud. Here you can see some molecular vibration lines at those frequencies, and this is the information that allows astronomers to find the composition of celestial bodies and the universe. But terahertz radiation is also attractive for other applications such as imaging. We can see that the terahertz wavelength is in the order of hundreds of microns. Because of this, the spatial resolution we can get is similar to that of the human eye. Also, terahertz is non-ionizing because its energy is only a few millielectron volts. Because of this, terahertz seems attractive for in vivo imaging applications, including medical imaging. We can see here examples of applications in dentistry and cancer detection, and security. Also, we can see that there is very important spectroscopic information at these frequencies, which makes terahertz interesting for either biological or chemical sensing. This is the typical transmittance versus frequency for two different DNA solutions, and we can see clearly differences. And terahertz spectroscopy setups can be easily integrated with microfluidic platforms for chemical and biological sensing. And let me finish the applications with communications. Terahertz can allow for larger bandwidth than radio frequency and microwaves. And it's also less directional and less susceptible to fog and scintillation effects than infrared waves. So from this point of view, there are several frequency windows in the terahertz range with not little, but enough atmospheric attenuation that can be used for short communication links. Actually, atmospheric attenuation is one of the big issues at these frequencies. Well, but not everything in the garden smells of roses. And not in vain, the terahertz range has been historically called the terahertz gap. And this happens because if we look, the device efficient sharply draws at terahertz frequencies. The physical processes in which devices operating at other frequency ranges rely usually degrade at terahertz, especially at room temperature. So it is very difficult to get, for instance, for a terahertz source, good output powers at terahertz. So there is a need for devices operating at room temperature capable of either actively manipulating terahertz waves or responding to terahertz frequencies. And we're going to see some ways in which in Notre Dame we have been trying to design these devices. So I'm going to start with reconfigurable terahertz components. In particular, I'm going to focus on devices behaving as modulators and switches. Okay? And these devices can find actually several applications, including power stabilization in terahertz sources, external modulators for terahertz band communications, arrays as reconfigurable patterns for imaging, and so on. In devices proposed to date achieving such operation, the reconfigurability is obtained either by changing the real or the imaginary part of an effective permittivity. Okay? And this can be done by several means, including optically, electrically, thermically, etc. From the point of view of application, electrically driven devices are perhaps the most attractive. So let's focus on electrically driven modulators and switches, and let's look at the literature, okay, where there are basically three types of devices, those based in two-dimensional electron gases, metamaterials, and MEMS. The idea behind the 2D-based devices is very simple. Let's consider that we have a piece of semiconductor which in principle is non-conductive. If we shine terahertz light, okay, whose wavelength is much larger than the semiconductor thickness, the material is optically transparent and the terahertz transmittance is 100%. Now, let's suppose that we start injecting carriers, okay? As we start injecting carriers, the material starts becoming more conductive. And so reflection and absorption process start taking place and transmittance drops. The material is turning more metallic. And in the limit, if we can get the material to have infinite conductivity, then it's going to be a perfect electrical conductor. Then the reflection is going to be almost 100%, no? And transmittance is going to go to 0. So basically, employing this principle, Thomas Klein-Osman, who is currently in the PTV in Germany, demonstrated modulators employing this structure. This structure basically consists of a metal gate gating a semiconductor heterostructure. By applying a voltage between the metal and the semiconductor, we can change the carrier concentration in the 2D, therefore its conductivity. And what we see here is that as the conductivity increases, the transmittance actually drops, but only at 3%. So what is the reason behind this, I would say, little modulation? Well, the reason is that the gate is a metal. Okay, since the gate is a metal, okay, we can see that, for instance, a 5 nanometer thick layer almost reflects more than 90% of the power. Okay, so this introduces a very large insertion loss. And also, it degrades the modulation depth, because modulation depth is proportional to the relative change in conductivity. And as you can see here, the denominator is going to be basically the conductivity of the metal, which is a constant, and a really large number. So this is the reason why these devices have very high loss and low modulation. One observation, okay? Actually, we would like a gate that is tunable. So in this way, we can potentially, under right bias, deplete all the carriers in the path of the beam. Okay? And that way, the insertion loss is going to be close to 0. So this is one of the design strategies we're going to see later. Okay, in order to overcome this problem, people have proposed to use the so-called metamaterial modulators. In these devices, there is a metal layer, you can see it here, which has 2 roles. First, it is an electrode, so it can control the electron density in some regions of the semiconductor material. And second, it is a frequency selective surface, so it can make the transmittance to be very sensitive to the electron density in some regions, therefore increase the sensitivity of the device. By employing this approach, people have actually achieved better performance, but there is still a very important trade-off between insertion loss and modulation depth. And finally, I'm going to mention MEMS-based modulators. In these structures, we basically, by applying a voltage, change the geometry of the device and therefore change its transmittance. When we look at the experimental demonstrations, okay, what we see is this, that in general, there is a trade-off between insertion loss and modulation depth. So our goal is to propose devices capable of simultaneously achieving high modulation depth and low loss. And we are going to see that by employing self-gated 2D pairs, together with some structure leading to electric field enhancement in the active regions of the device, we can achieve this. So let's look at our material system, which is graphene. As you might know, graphene is a 2D semiconductor, that means atom thick, which is composed of carbon atoms. These atoms are arranged in an hexagonal lattice. If we look at reciprocal space, the structure of graphene is also hexagonal, and we can see that at the edges of the first brilliant zone, these points, graphene has a linear EK dispersion. What does this mean? Carrier effective mass is the second derivative of E with respect to K. We said E versus K is linear, so effective mass is 0. This means that carriers in graphene actually are massless. In practice, okay, this translates into that we get a very high mobility for both types of carriers, electrons and holes. And this is the reason why graphene is the subject of a lot of attention for high-speed electronic devices. So let's look at its optical properties. Here, I am showing the band diagram of graphene under two different bias conditions. This dashed line represents the Fermi level, which basically indicates the energies up to where electronic states are occupied. So the gray shaded line represents field electronic states. If we shine light, it can be any type of light, electrons can absorb that light and jump to higher energies. When those jumps are from valence to conduction bands, we call them interband transitions. When they are between a band, as shown here in red, we call them intraband transitions. And in the terahertz photon energy is only a few millielectron volts, whereas the energy needed for an interband transitions is in the order of hundreds of millielectron volts. So from this point of view, intraband transitions are the dominating optical phenomena. And we can see that as the Fermi level becomes closer to this point, the Dirac point, the density of states available for intraband transitions, the number of electrons who can jump decreases. So that means that the optical conductivity also decreases. So this is the operation mechanism in which we control the optical properties of this material in the terahertz range. So let's look at one device implementation, a device capable of modulating the terahertz transmittance. Let me start by the fabrication process. Okay? Our graphene is grown by the copper catalyzed CVD approach. This was grown by Sabrina Rafik and Michelle Kelly in-house at Notre Dame. Most of our devices are built on silicon substrate. And what we follow is basically a standard MOS process where we thermically ground silicon dioxide, then deposit metal into the back of the substrate so we can electrically contact there. This metal can be potentially patterned depending on the application. And then we transfer graphene into the top by means of PMMA and wet etch methods. Finally, metal contacts are deposited into the graphene. The final device structure is shown here. Okay, and the idea is the following. First, the silicon wafer is chosen as a very highly resistive, lightly doped, and the metal contact is patterned into a ring shape, so there is not any big loss in the path of the beam. The idea here is the following. By applying a voltage between the graphene and the substrate, we can control the carrier density in the graphene, okay, and in the silicon dioxide silicon interface. As carriers of one type accumulate here, carriers of the other type will accumulate here since those two layers are capacitively coupled. Okay, we are going to neglect the effect of the carrier dynamics in the silicon. And this, you can assume that is a result of the silicon mobility being much smaller than that of graphene. You can look for a careful discussion of this in our latest Optics Express paper. So what we see is the following, that by increasing the applied voltage, graphene transitions from being p-type, therefore having a large density of states for intraband transitions, to intrinsic. And as a result, the transmittance goes from low to high. In these devices, the insertion loss is given by the minimum DC conductivity of graphene, and this is around 0.2 dB. The modulation depth depends on the achievable DC conductivity swing of graphene, so we want graphene with very high quality. And the speed is given by the RC time constant of this device. Our experiments basically shown around 16% modulation of the transmittance when applying a voltage, and modulation speeds up to 20 kilohertz. This is limited by the quality of the CVD graphene we are employing, okay, and in the future, as growing methods improve, we will expect this performance to improve. Okay, but as you can imagine, this performance actually is very distant from what we need for real-world applications. So we have proposed two approaches in which to achieve a better performance. One is by employing the so-called active metamaterials. And here the idea is to take active graphene in conjunction with a passive frequency selective surface. For instance, the frequency selective surface can be metallic structures with a periodical pattern. Okay, these structures behave as terahertz bandpass filters. When we look at the frequency at which the transmittance through the structure is maximum, okay, and when we consider the electric field profile in planes parallel to the plane of the FSS, what we see is that as we increase the distance, okay, the electric field profile dramatically changes. First, very close to the FSS, we see that the electric field is greatly enhanced in some regions right below the slot. And this is because all the terahertz power has to pass through the small aperture. Also, when we look at the Poynting vector, we see that it has very strong components parallel to the direction of the FSS. Okay? However, far away from the FSS, there is a uniform electric field distribution, and Poynting vector basically points normal to the plane of the FSS. So when we look at the placement of an active graphene layer, we see that if we place it too close, then the transmittance becomes very sensitive to graphene conductivity. And actually, for the typical conductivities on graphene, transmittance is practically zero, and the structure turns to be 100% reflective. However, if we place it very far from the FSS, then the electric field does not get altered, so the behavior of the device is the same as that of the one we just saw, and so its modulation depth is limited to a 20% maximum with the current typical quality of graphene. So taking that into account, we look at the transmittance versus conductivity and analyze this for several placements of the graphene layer. We see the following. Very close, we have very large modulation depth, but very large loss. Very far, we have low modulation depth and low loss. So there is an optimum. And for a 1 terahertz design, the optimum happens when the active layers are placed 10 microns away from the FSS, and in that case, we can achieve 1.5 dB loss and 90% modulation. So let's look in practice what happens if we place the graphene very close to the FSS. And here, we are going to look at this work by Boon Ki-min's group from South Korea. Okay, and what we see is this. Here, they place their graphene right next to the FSS. And you can see that there is a very large modulation. In this case, I think something like 80 or 90%, but at the expenses of a large loss, as we discussed. So basically, by cleverly engineering these structures, one can achieve a performance in terms of insertion loss versus modulation depth superior to that of the current art. And we perform a simple experimental validation employing a polyimide as substrate and spacer, a frequency selective surface basically that we obtain by evaporating aluminum and stacking graphene. Okay, and what we see is the following. When we look at transmittance versus frequency for a fixed graphene conductivity, we clearly see that as we place the graphene closer to the FSS, the transmittance at this peak transmittance frequency decreases. And when we look at transmittance versus conductivity, we see that it actually decreases in accordance with theory. Here, the continuous line are HFS simulations. The points correspond to measured data. And the measurements and theory, I would say, clearly match. But there is another way in which we can also achieve a good performance, and that is by modulating the terahertz reflectance. The device structure is similar to that of the first device I introduced, but with a difference. Now we have a uniform metal layer in the back which has two roles. It is an electrode and it is also a reflector. Because this layer being a reflector, when we look at the electric field profile, we see that the electric field exhibits a node there. So the electric field in the active graphene is going to depend on the substrate thickness and the terahertz wavelength, only on those two things. And we actually notice that there are two extreme cases. If we place the graphene as, at a distance which is an even multiple of a quarter wavelength, when the substrate thickness is an even multiple of a quarter wavelength, the electric field in the graphene goes to 0. However, if we place it so that the substrate thickness is another multiple of a quarter wavelength, then the electric field is maximum. So when we look at reflectance versus graphene conductivity, we see the following. For the first case, when substrate thickness is an even multiple of a quarter wavelength, reflectance is always 100% and totally insensitive to the graphene conductivity. However, in the second case, when the substrate thickness is an odd multiple of a quarter wavelength, there is a clear dependence on reflectance with conductivity. And this is a very sensitive dependence. When we consider the conductivity swing of typical quality CVD graphene, we compare the modulation depth in the reflectance structure with that in the transmittance structure, we see that 4 times more modulation is achievable in the reflectance structure for the same conductivity swing. And you can actually justify this mathematically employing the ABCD matrix formalism. You can derive equations for reflectance as a function of frequency and all the geometry parameters. These equations can be greatly simplified for the case when the substrate thickness is another multiple of quarter wavelength, and they take this shape. And we see clearly in the numerator of this expression that reflectance can actually be 0. And this happens when the graphene conductivity is matched to the inverse of the vacuum impedance. So this is the unique property of these devices. These devices can achieve complete terahertz absorption, and this is tunable. And this is something that I would say is not possible by other approach. Basically, we went ahead and construct one of these samples to see which performance we can get. Here I am showing the characterization of the silicon wafer. Okay, the silicon wafer is highly resistive, and by performing terahertz transmittance measurements, we found that the frequency at which substrate thickness is another multiple of a quarter wavelength in the frequency range where we can measure is around 620 gigahertz. Let's remember this number because we are going to expect to see all the fun happening at these frequencies. Okay, we constructed our sample. Here you see an optical image, and we measure the reflectance. And what we saw is the following. Let's look at reflectance versus frequency, and let's start applying voltage. Okay, we see how reflectance starts dropping. And at the end, we got 64% and 2 dB insertion loss. Okay, we couldn't get to completely absorb all the radiation because the quality of the graphene that we have in-house so far is not so good. But this overall is a very, I would say, encouraging performance. You can see that this performance is pretty much comparable or better than that of the previous art, with the perspective of, by improving the graphene quality, getting close to 100% modulation depth and decreasing the loss. So based on these results, we look at the system integration into a simple prototype imaging system. The device basically consists of an array of 4x4 reflectance-based modulators. Each of these elements can be independently biased. So in this way, we can get images up to 16 pixels. Here I am showing a picture of our optical setup. We have the terahertz radiation coming from a terahertz source going to the array. When it gets to the array, each element of the array controls a region of the reflected beam. Then this beam gets collimated, and we get a collimated pixelated beam of illumination in the plane of the object. And this object can be basically imaged by turning on and off each element of the array. You can look for details in our latest Optics Express paper. And here I am showing basically the shapes of some objects that we place and the reconstructed images. Okay, this is, I would say, just a prototype device. The performance still needs to be optimized, but this is, in my opinion, a very encouraging result. And something, I would say, nice about these devices is that we can get video rate images up to 400 pixels. So now let's switch gears and let's see high-frequency electronics based on new electron transport mechanisms. The idea here is the following. The speed of devices and systems is limited by the velocity at which we can move carriers. Okay? In optical systems, this is the speed of light, in the order of 10 to the 10 centimeters per second. But in electronic circuits, in transistors, this is the electron drift velocity, which is 3 orders of magnitude lower. So we want to address how to achieve devices operating at speeds larger than what is limited by the electron drift velocity. In a traditional low-frequency model of a high electron mobility transistors, in the linear region, when BDS is close to 0, we see that the carrier density is pretty much constant and depends, therefore, very lightly on the position along the channel. However, at high frequency, we see that we should treat the channel conductivity with some frequency-dependent model, for instance, root model. Okay, that means practically that the channel resistivity has an inductive component. Also, the gate provides for a distributed capacitance and conductance. So these devices at high frequency are basically transmission lines. And you can actually calculate their parameters and model them. We notice the following. Since these devices are transmission lines, the voltages along the channel, the currents, the electron velocities, and the electron densities, therefore, are waves. So what we can see is that waves of electron density can take place on the high electron mobility transistor channels. And when we look at their group velocity, I'm not going to justify this here. You can look in my papers. You can see that this can be 10 times larger than the electron drift velocity. So from this point of view, in these devices, we can potentially achieve transport associated with terahertz transit times. Okay, this is basically so far not our novel idea. Michael Schur actually proposed to use this phenomena for detection, mixing, and frequency multiplication of terahertz radiation in the mid-90s. Okay. actually, this is a pretty popular topic nowadays. Last year alone, there were 200 articles dealing with devices employing this physical process. I want to mention this, Daiichi Otsushi, a close collaborator from Tohoku University in Japan, demonstrated last year the terahertz detectors, operating, employing this phenomena with the largest room temperature, responsivity, and lowest noise equivalent power. So far, these devices are already between the best terahertz devices. Okay, and what is our fundamental contribution and idea? That we are proposing a way, in a new device concept, we can actually amplify terahertz signals based on this phenomena. And this is because the fact that we are adopting a gate stack with a negative differential resistance. Okay, let's look from where does that come. We said that we have this transmission line model. The transmission line propagation constant has an attenuation term. Actually, this term is large, which means that the electron plasma waves normally damp very quickly. In silicon, this is in the order of tens nanometers. In HEMS, for instance, in gallium arsenide or gallium nitride, can be in the order of hundreds of nanometers. But we also notice the following. If we engineer correctly these structures, we can actually even achieve no attenuation. In the case when RC is equal to minus LG, where RC and LG come from the transmission line model, the real part of gamma goes to 0. And when we look actually to the model of the HEM conductivity, what we see is that the gate has a very important role. Actually, if we get the gate capacitance over the gate conductance to be in the order of minus tau, where tau is the electron momentum relaxation time in the channel, we can completely counteract the plasmonic losses, the attenuation due to electron scattering. So engineering the gate stack is key. Okay? And we need, this means that either C gate or G gate need to be a negative number. Okay? And in semiconductors, we can actually easily achieve a negative differential resistance, for instance, employing double barriers. I'm not going to go through the details of why this has a negative differential resistance, but this has been demonstrated, and the transit times through these double barriers are above 1 terahertz. It's like these transit times are, I would say, friendly with terahertz frequencies. So based on this phenomena, again, I'm not going to go into the details, we have demonstrated via simulations that in detector configurations, we can achieve very sensitive terahertz detection, more sensitive than what people can achieve employing normal HEMS. And as I told you, that is already a record. So these structures promise for the best responsivity at room temperature. And also, under right circuit configurations, again, I'm not going to go through these details, we can actually get a stable power gain at terahertz. And in our IEEE transactions on terahertz science and technology paper, I have demonstrated that a 100 nanometers device, properly engineered, can provide a stable gain at 4 terahertz up to 5 dB. Okay, and actually, by employing some techniques, better performance can be obtained. This is just an example. So let's look, based on this work that I have done, some future research directions. One direction that I am envisioning is to develop reconfigurable devices, more devices for terahertz beam steering. I actually want to target all the ways of beam steering. That means control the focusing and beam bending. And this can have a lot of applications that I'm listing here. Like in imaging systems, we can make compact, integrated cameras, everything on a chip, and planar, and also in communications. And the idea will be to use metamaterials following the work by Federico Capasso about the generalized laws of refraction and reflection. There he shows that when we have a metamaterial where each element is rotated at a variable angle, okay, we can actually bend the terahertz beam if the angular dependence on space is linear, or focus if we have a parabolic dependence. Okay, and actually at terahertz, in the way I already showed you some devices, we can engineer these structures to be reconfigurable by employing semiconductor materials and, I would say, cleverly engineering electromagnetically the device. So in this way, I'm not showing exactly how. We can, for instance, by means of optical excitation, potentially switch a beam between collimated and focus, or we can perform this by means of electrical control, employing the semiconductor material of your choice, which in my case may be graphene. So this is, I would say, a very important research line, since this type of device so far do not exist in the terahertz range. And the second research line that I am envisioning is develop active plasmonic devices based on graphene, for instance, for allowing gain at terahertz frequencies. What is nice about this? That only 2 graphene layers separated by an insulator can provide us, only these 2 graphene layers, okay, can already provide us for negative differential conductance. And you can look, if you wonder about this, in Dev Shina's paper in DRC 2012. So this structure can be modeled in AC, high frequency, and by nature it's going to be an active transmission line where the graphene is going to provide us with the negative differential conductance counteracting the electron plasma wave damping. And once we have this, we can actually have a lot of fun. We can have plasma waves in semiconductors propagating for hundreds of microns, playing with the interaction between those plasma waves, providing gain, and we also have the possibility of having a complete active control over all the properties of these devices. So this is, I will say, kind of a conclusion slide. We see the device, reconfigurable devices that I have proposed and demonstrated. My proposals in terms of devices allowing amplification, where I want to go and how I plan to integrate everything together into systems like compact terahertz imaging or communication systems. So I would like to thank my group in Notre Dame. I really found great collaborators, great students and friends, and this work would have been impossible without the help of all these people. And I would like to thank you for your kind attention. So I am available for questions.
Any questions?
On your modulators, you showed just one slide that showed a bandwidth curve, and it looked like the switching bandwidth was less than 100 kilohertz.
Oh, yeah.
Is there any intrinsic reason for that?
For this is the large area of the graphene. And actually, you can make it a lot faster than that. Okay, do you remember the metamaterials? You can make the graphene only to have the shape and the size of the, let's say, of the frequency selective surface slot, okay? And that is a small area of all the active area. If you do that, you can make the calculations and see that you can improve the speed and get up to gigahertz, okay? So by reducing area of the active device is a way in which to increase the speed. And actually, at this point, that is, I would say, the way that I think that is going to most likely work. There are other approaches which might also give you better switching speed. Okay.
So, a couple questions. First of all, is it because of the area of the graphene, or is it because of the volume of the silicon under it, which gives you the large density?
Yeah, you're right. I would say the silicon, the capacitance also is important. Okay, but the thing that happens is that when you are switching between low conductivity and high conductivity is kind of when the graphene is resistive, that is very resistive. You have a dynamical resistance changing, and that is actually a pretty big number. So in this case, that is, I would say, the main component. Yeah.
So about the graphene, how do you buy it from Notre? Do you make it through exfoliation?
In this case, this is CVD graphene, and it is grown in Notre Dame. Okay, at the beginning it was grown in Notre Dame, but then we got it from collaborators in Peking University. Kind of our grower left at one point.
So how do you know that it's single layer, not bilayer?
Oh, Raman.
Huh?
Raman, from Raman spectroscopy you get.
You actually check it before.
Yes. Yes.
The last question I have is sorry.
Go ahead.
Are there other, there's been a lot of work on graphene and these two-dimensional materials, and the lack of a band gap is usually good for some things, but there are some other newer materials like molybdenum and sulfide, which have a band gap. Do you think that those might be preferable for some of the things?
Okay, for the things that I am doing now, okay, in terms of terahertz, I don't like that those materials have lower mobility, so their conductivity swings, and therefore strength is going to be smaller. Okay, so from that point of view, although they are two-dimensional and have the same, I would say, characteristics, I think that I still prefer graphene.
Now you project a gain of 5 dB in a device. How did you come up with that number? What does it depend upon?
Oh, that actually, I would say, depends basically, at the end, on all the device structure, because there basically I run an optimization, and I basically optimize, in this case, fix the material system. I optimize the geometry of the structure. So from that point of view, I kind of solve blindly and relied on the number that the computer gave me.
So you're counting on negative conductance.
Yeah, and that actually, something.
Per cell.
Yeah.
For each of these cells.
Yeah.
There's a certain amount of negative conductance.
Yes. Yeah, and for that, I actually simulated that by employing Schrödinger-Poisson equations. Okay, so I have as a function of the voltage that I apply the negative conductance in the gate. Okay. And what I did is I put everything together into an ADS model and made optimization there.
So how could one increase this negative conductance?
Oh,
so that you can.
If you want to increase it, one way is having materials who have larger mobility in the barrier. I am simulating and analyzing this in gallium nitride. Let's go to the arsenides. That way you might get better.
Any last questions? One more?
Yeah.
Are your predictions towards the end about the gain device and such? Did you consider velocity saturation?
Oh, in this model, I would say velocity saturation or those things do not play at all, because I don't have any current. It's like all the transport is via the plasma waves. It's like you don't have, let's say, single electron transport. Those things, I would say, do not matter in the model, because the electrons are kind of cold in this model. And this is the reason why Otsushi has very low noise equivalent power in his detectors, I think.
Okay, any final questions? Thank you very much.
You're welcome. Thanks.